Assalamualaikum and good morning, afternoon, evening, depending on where you watch when you're watching this. We are group 2 from the subject vibration and we are doing force damp vibration analysis using MATLAB. Our team consists of Pen Sen, Aman Farhan, that is me, Ahmad, Danish, and Mohamad Faiz. Sadly, one of the group members could not make it, so we are covering their part. So first of all, the first problem overview, our objective is to analyze the dynamic behavior of a single degree of freedom system under forced vibration with damping. So basically, this is what the system looks like for our question. And the system setup consists of mass equals to 5 kg, spring constant equals to 1000 Newton meters, forcing functional is sinusoidal at 4 times with nature of frequency, and damping ratio varies of 0 to 1. Our equation consists of mx double prime plus cx prime plus kx equals to f sine omega t. So our solution on settling this problem is numerical solution using ODE 45, molecular function with parameter suite over damping ratio, GUI with animation and interactive plot, additional 3D surface plot for sensitivity. All these methods were later explained in the slide. The case for the system when simulated, there are 3 cases. There's under damp, which is under 1, critical damp is equal to 1, and over damp, which is over 1. It is shown in the slide.
Assalamualaikum. My name is Ahmad Danish. Okay, so for the key result, firstly, we observe the behavior of the system under various data ratio. In the undamped case, the system oscillates indefinitely with high amplitude. This means that without any damping, the system keeps oscillating and does not settle to equilibrium, which is unrealistic in most practical situations. As we increase the damping ratio, we see a reduction in the amplitude of oscillation, and the system settles to a steady state more quickly. This is especially noticeable with low damping values. For example, when the damping ratio is 0.1 or 0.25, oscillations still occur, but at a diminished amplitude, and the system returns to equilibrium faster than the undamped case. When we hit critical damping, the system achieves the faster return to equilibrium without oscillation. This is the ideal case in many engineering applications, as it prevents the system from oscillating while still allowing it to return to its rest position as quickly as possible. Then we also created 3D surface plots to visualize how displacement change over time for each damping ratio. This plot shows a clear trend of damping suppressing oscillation motion. As the damping ratio increase, the displacement decrease and the system stabilize more efficiently.
Okay, now see the videos, the demo, the MATLAB demonstration. Okay, now start. As you can see, the system keeps oscillating with the larger amplitude and never settle. So in the start with the damping video, so now we increase the damping, the amplitude increase and the system settle faster. Here is the critical damping case. It returns to the equilibrium quickly without the oscillations. So this one is our MATLAB GUI to follow the rubrics. So next. This one is our answer the questions, force response to the different damping ratio, and this one is comparison of the force damping ratio response and the 3D visualization of the response as the time and domain damping ratio. Okay, so next. Real world relevance presentation. So in the application in automotive substantial system shock absorbed reduce the vibration and the improve conforms. In the civil engineering, turns the mass dampers in the buildings of and bridge, reduce the wind and seismic vibrations, external force. In rotating mechanically, damping prevents the excessive wear and the dangerous resonance. So, in the engineering impact, this understanding help engineer turn damping for the different applications. It improves the safety, performance, and reliability across the multiple engineering field. Our simulation provides a clear way to visualize and evaluate this effect before the building physical system. So next, in the conclusion, this MATLAB project allows us to visualize how the damping affects vibrations behavior compared to the undamped damps, critical damps, and the overdamped response. Performing the sensitivity studies using the 3D surface plots, also and build the interactive GUI for the better demonstrations. It shows how the simulation tools like the MATLAB can support the design, the decisions, and the enhanced understanding, and the bridge store theory with the practical applications. So that's all. Thank you for your attention.